Sunrise, October 9, 1985. Hermit Rapids, Grand Canyon, northern Arizona. A United States Geological Survey research team has camped at this rapid overnight. In the pink rays of sunrise that portend an autumn storm, we are looking for a site to set a time-lapse camera to monitor the waves in the rapid. The time-lapse camera will record the hydraulic behavior of the rapid as we go about our day's work of surveying, boulder counting, fathometer measurements, and filming of boats and floats going through the rapid. The water entering Hermit Rapids this morning left Glen Canyon Dam about 13 hours ago. Discharge of the Colorado River into the Grand Canyon has been controlled by the dam since 1963. In the next 1.5 minutes of time-lapse film, you will see 6 hours of conditions at Hermit Rapids. The members of the field crew will appear and disappear like frenzied ants running across the boulder field in the foreground. Note the standing waves on the major jet of water entering the rapid from the right of your screen. Note the eddies on both the right and left sides of this jet at the bottom of the rapid. And above all, note the clouds in the sky that are going to cut this filming effort short. In spite of a century's work in the Grand Canyon, there has been little documentation of the hydraulic behavior of the rapids. Work was begun at Crystal Rapids by the USGS in 1983 in cooperation with the Grand Canyon National Park Service and the Bureau of Reclamation Glen Canyon Environmental Studies Project. The goal of the study was to document and to interpret the hydraulic and geomorphic relations at the major rapids. Quantitative measurements are difficult. The rapids are large in scale, turbulent, and present formidable logistics problems for instrument launching and recovery. Because the river is so large, filming of floats and analyzing their trajectories on movies is difficult. For example, there is a small, bright pink float wending its way through House Rock Rapids from left to right in this scene. Bright orange and green striped stakes that are 6 feet in height have been placed on the far shore, and the trajectory of this float will be reconstructed using the measured positions of these stakes and other obvious rocks and ledges. Although sophisticated telemeter devices have been invented to serve as hydraulic floats, the instrument of choice for use in the harsh environment of the Colorado River Rapids was a sand-weighted children's punch bag 3 feet in height. In total, we found 20 in all of northern Arizona and bought them on sale for $2.99 each. Because the emblem painted on their front surfaces resembled a certain Yogi bear, these floats became affectionately known as our Yogis. The systematic launching of these Yogis at prescribed positions above rapids has provided the first internally consistent set of velocities and streamlines in the rapids. We have measured Yogis to be traveling up to 7.5 meters per second or 25 feet per second in the middle of some rapids. The first float that you saw followed a path over shallow water that crosses the toe of the debris fan from Ryder Canyon. This second Yogi was launched much further to the left side of the rapid and follows the flow down the main channel and into the largest obstacle at House Rock Rapid, a wave caused by a rock in the channel. In the foreground, note the typical configuration of a rapid that you will see over and over on these films or on a river trip: a major debris fan that pushes the channel of the Colorado against the far wall, a large eddy, and a debris fan and sandy beach. Here at 24.5-mile rapids, you see a debris fan in the foreground. It has pushed the Colorado River against the far wall, narrowing the channel to about 1/2 of the upstream width. This debris fan, like most of the major ones, was probably large enough to have completely dammed the Colorado River. During large floods that surged down the river before Glen Canyon Dam was emplaced, the water velocity became sufficiently high to clear a channel back to about 1/2 of its normal unconstricted width at these places. Hance Rapids has the typical hydraulic features of most rapids. Above the rapid there is a calm backwater. The dory approaching the rapid is just leaving this backwater. Underneath the dory, the channel bottom is rising rapidly because the dory is approaching the upstream side of the debris fan from Red Canyon. Simultaneously, the channel is reduced in width by the debris fan. The shallow depths in the upper parts of rapids can be major problems to boat navigation. In particular, Hance Rapids and Horn Creek Rapids are formidable obstacles at low water, and at flows much below 5,000 cubic feet per second are nearly impassable to the larger motorboats used by commercial trips. The dory here is threading its way down the left side of Hance Rapids, a route impossible for larger boats. The rocks that you see in the foreground are formidable obstacles for the river to move. Velocities of about 30 feet per second, or roughly 20 miles per hour, are required to move a boulder that is 3 feet in diameter. Notice that the rocks that are being so circuitously avoided by this dory are generally larger than 3 feet in diameter. The absence of small boulders means that at some time in the history of the Hance debris fan, the water of the Colorado has moved more than 20 miles per hour over this area. On the far wall of the Grand Canyon, a spectacular dike of volcanic rock cuts diagonally up through the red shale. Large motorboats, such as the one approaching the rapid in front of the dike, must generally follow the main channel through all rapids, because they cannot get through the shallow flow that crosses the debris fans. Hance Rapids is a particularly difficult rapid for the large boats because the main channel against the far right shore has some very large boulders in it. Thus, this motorboat is threading its way down a tortuous secondary channel. As the camera pans down the rapid, notice the prominent line of acacia and mesquite bushes on the far wall of the canyon. Prior to the closure of Glen Canyon Dam, large floods every few years brought the river up to the level of these bushes. For 20 years, between 1963 and 1983, the river never approached this depth. In the spring of 1983, rapid snowmelting in the headwaters of the Colorado forced discharges through Glen Canyon Dam to nearly the height of these bushes. These movies of Horn Creek Rapids will show the launching of 3 yogis. This first one takes a streamline down the tongue on the north side of the river. Note the lateral waves that define the tongues and separate the smooth entry water from the roiling water in the rapid. As the water flows from the backwater into the narrowed channels at constrictions, it accelerates. The flow regime changes from a condition called subcritical to a condition called supercritical. The important difference between these two flow regimes is that standing waves cannot exist in subcritical flow, but can exist in supercritical flow. We attempted to position the yogis to enter specific parts of the flow field. This requires great skill on the part of the motor boatman, who must hold the boat from an unscheduled trip down the rapid, while selecting just the right streamline for the yogi. This second yogi was launched on a streamline that took him precariously close to a big hole near the horns that give Horn Creek Rapids its name. By the time the yogi accelerates down the top part of this rapid, he's going to be going about 7 meters per second. The terms subcritical and supercritical are the hydraulic equivalents of the terms subsonic and supersonic in gas dynamics. And, just as shock waves, sonic booms, or standing waves can occur in supersonic flow, so large amplitude standing waves can exist in shallow water supercritical flow. In hydraulics, these are called hydraulic jumps. On the river, they are called variously the lateral waves, oblique waves, compression waves, or haystacks, depending on their position in the rapid. This third yogi was launched in the backwater above Horn against the far south shore. From his slow approach to the rapid, you can get a feel for the low velocity that is characteristic of backwaters. Why are there backwaters at rapids? If all of the discharge could be accommodated in the constricted channel at a rapid as subcritical flow, there would be no backwaters. Water would flow in the main channel, accelerate through the constriction as required for conservation of mass, and then decelerate in the diverging part of the channel. All flow would be subcritical and there would be no major rapids. Calculations suggest that such subcritical conditions can only be obtained at low discharges for the channel of the Colorado River, perhaps well below 10,000 CFS. At higher discharges, the discharge cannot be accommodated in the constriction with the available head or total energy for the flow, and water ponds upstream until sufficient head is built up that the discharge can be accommodated in the constriction. Some of the backwaters on the Colorado River are over 1 mile long. As the camera sweeps down Hermit Rapids in the next scenes, note the smooth rolling waves on the tongue of the rapids and the series of 5 breaking waves below the tongue. The oblique hydraulic jumps that form the lateral waves of the tongue crisscross the channel and reflect from the channel walls or eddies in a more or less regular pattern. In a laboratory flume, a nice pattern of X's or diamonds would be seen, but this pattern is rarely so well defined on the river. The waves are highest where the individual standing waves intersect. These tall waves are dubbed haystacks by river runners. The ride off of the rollers onto the haystacks at Hermit Rapids is one of the most beautiful rides on the river. By the way, this skilled kayaker was in charge of retrieving yogis so that they could be used over and over for the velocity measurements. In general, with increasing discharge, waves in the channel first grow in amplitude and then decay in amplitude at high discharges. This is the so-called drowning out of a rapid as the flow gets deep enough that supercritical conditions change to subcritical. Most of the rapids associated with debris fans that had been emplaced before Glen Canyon Dam closure, and therefore which had been worked on by natural floods, wash out at discharges approaching 100,000 CFS. One rapid did not drown out, Crystal Rapids. You will see here 2 motorboats go through Crystal Rapids in 1979. Note how close to the far wall of the canyon we seem to be standing as we watch this boat. The debris flow on which we are standing formed in 1966, after Glen Canyon Dam was closed. This debris flow severely constricted the channel. In contrast to constrictions on the order of 0.5 elsewhere in the canyon, here at Crystal the channel was constricted to only 1/4 of its upstream width. Crystal was a difficult rapid during 1966 to 1983 because of a large rock and hole in its narrowest section. In 1983, more water flowed through the channel at Crystal than ever before in its history. In this sequence, the discharge is 60,000 CFS. Unlike other waves on the river, the old Crystal Hole did not wash out as the discharge increased. Instead, it became a gigantic chasm and wall spanning nearly the entire channel width. At 60,000 CFS, there was only a narrow margin on the north side of the river where a boat such as this might hope to pass the hole. This wave forced the National Park Service to close Crystal Rapids to commercial boating at this discharge level. Flow velocities became so high that even the largest boulders in the channel at Crystal Rapids could be transported, and at about 60,000 CFS the channel began widening and headward erosion occurred. The erosion processes that used to take place under natural flood conditions were now beginning at Crystal Rapid in 1983. The scenes shown here are at the maximum discharges of 1983, about 92,000 CFS. You will see 2 kayakers. The first flips in a strong curling wave that marks the flow boundary between the main current and the strong eddy that sits in front of Slate Creek. That strong curling wave upstream of the main Crystal Hole is a remarkable phenomenon. It is the shear zone between the Slate Creek eddy, shown here, and the main current, and it has become so strong that water is tossed as much as 10 feet above the river. Do you remember how close the camera person was standing in the first shots that you saw of the motorboats here in 1979? That camera was out beyond any of the remaining vegetation that you can see here. The Crystal Creek debris fan has been completely overtopped by the 92,000 CFS discharge, and much of the salt cedar vegetation has been stripped from the debris fan, and boulders are thudding and booming out in the main channel. The second kayaker starts much further left in order to sneak behind the Slate Creek eddy fence. He successfully navigates this region and sees the front side of the Crystal Hole, but not the back. The 1983 high water substantially changed Crystal Rapids. This footage was taken in 1985 at a discharge of about 45,000 CFS, and it shows the new waves near the head of the rapids. Erosion during the 1983 flood concentrated most of the drop through the rapids at the top, forming the conditions for a strong hydraulic jump on the top right side of the rapid. This boat successfully navigated through the top waves, but just flipped in the old Crystal Hole. The double punch of the two prominent waves causes about 1 out of every 4 non-motor boats to flip when discharges are in the range of 30,000 to 40,000 CFS. Note the open feeling that one gets upon arriving at Dubendorf Rapids after emerging from Crystal, and remember that the constriction at these mature debris fans is 0.5. During the 1983 floods, the channel at Crystal widened to about 0.4 of the normal channel width. Calculations suggest that floods on the order of 400,000 CFS would be required to erode the channel at Crystal to the value of 0.5, characteristic of the older debris fans. Therefore, under the controlled discharges of Glen Canyon Dam, the channel at Crystal Rapids will stay more tightly constricted than the channel at the more mature debris fans. Most of the concepts of supercritical flow discussed here were developed to explain the events at Crystal Rapids in 1983. Our ability to interpret the river was severely limited by lack of documentation of the channel at Crystal Rapids. In collaboration with the Bureau of Reclamation and the National Park Service, we have been able to obtain data on the debris fans and the channel at the 9 rapids you have seen here, plus several others. To study and map these rapids, we have made 2 river trips spanning nearly 5 weeks. Even with as much as 40 miles per day on travel days, we have averaged less than 2 days at each rapid. Survey control points were put in at each rapid, and hydraulic maps of the rapids and their debris fans are being prepared at a scale of 1 to 1,000 with 1 meter contour intervals. The size distribution of the largest particles was measured so that we can estimate the discharges required to move the boulders and clear the channel. Water surface velocities and streamlines are being obtained from the floats. These data are being integrated with other geologic projects and with studies of aquatic and terrestrial biology and of human recreational usage to help managers of the river corridor in their efforts to preserve the unique environment of the Grand Canyon.